Yeah. So in the last class, we have been talking about the MOSFETs. So I'll just list out what we have done. Yeah. So we were looking into this mass structure, and then we had also spoken about this region of operation, right? And along with it, we also were looking at the current equations, the drain currents in each of these regions. Okay. After this, we were just looking at this CS amplifier with a resistive load, right? And let me try to recollect what we have done for this particular part, so that it will act as a base for the coming discussion. Okay. So we defined this Vout, output voltage, as something like VDD minus the current through the value of resistance. So this is what we have seen, and we also did. So this was the output expression that we had realized for this network, and what we did is that we were varying this value of input voltage right from 0 to all the way to VDD. Okay. Now, when I do this, what happens is that the variation in my VI is actually affecting the current, and because of this, my Vout is getting varied. Okay, so there is a kind of relation that goes from VI to I and from I to output. Okay, so that is how the variations were happening. Now one could actually discuss the same phenomena by making use of this output characteristic graph. So what we said is that I just write down this Vout expression. Now, when the input voltage is at 0, the VGS of this particular structure would then go to 0 as well. So under this condition, our transfer was in cutoff, and what I said is that it is not only this particular origin as the cutoff region, it is the entire region is assumed to be a cutoff. Okay, and throughout this entire region, what happens is that the Y value, which is nothing but my ID, is completely 0. Okay, so we have to take the entire regime whenever the transfer is in cutoff, right? And also for this, when I try to substitute, I was getting a value of Vout which is equal to VDD, just because the ID is completely equal to 0, and this Vout is nothing but the voltage drop across my drain to source potential. Okay, and because this graph is basically ID versus VDS, I can just pick this value of VDD and then I can just fix it over here. Okay, and this is what we did. Now, as I increase the value of VI beyond VT, so what happens is that the transistor slowly turns on, and due to which there is a small amount of current, and that current could be represented by something, a kind of graph that goes something like this. Okay, so there is a very small amount of current that happens when I have the value of VI which is a little bit greater than the value of VT, and due to which there is a small current. And when this quantity is quite small, the Vout that I would get for the new value of VI that I have applied is slightly lower than the value of VDD that I was getting before, right? So due to which I just want to plot this value onto this VDS axis. So what I did is that from the previous value, which was at VDD, I just lowered the value by a small quantity, and that would intersect this current graph at this particular point. Okay, and this discussion continues. Like, as I keep increasing the value of VI more and more, the current would then start shooting up, and due to which the Vout would then keep falling. Okay, and that is the physical phenomenon that happens. But also there is something that I just want to exploit here, is that you could be able to see that the value of VGS that I have incremented in each of these cases were at a rate of 0.5. They are incremented at equal steps. But what about the currents? Are they incremented in the equal steps, or do you find some sort of differences in the spacing between them? Yeah, so why is that difference happens? Yeah, because the current in the saturation region is basically defined as K dash W by L, and then VGS minus VT the whole square. And because of the square relation, you would find that the current is actually has a quadratic relation. So as you increase the value of VGS in terms of equal steps, the currents will not be of same step or similar equal steps. Okay, they will have an unequal steps here, just because of the square relation. Yeah, so we will not mind that. So what I did is that, like, because of this relation, as I increase the value of VGS, the current is keep rising, and because of which the Vout is keep stepping down. I just try to mark each of these points, and then at a particular point, so probably I will just choose a particular point here such that it intersects at this particular node. So now at this particular, for a particular value of VGS, you could be able to see that right from cutoff, I just jumped into saturation, and all the way I have moved in the saturation region at a particular point, and this is a special point where I am at the edge of saturation, right? For the corresponding input, I am currently at the edge of the saturation, and the corresponding output voltage could be read just by taking down this particular value, and then I could read that to be around 2 volt. Okay, so that is my VDS corresponding value. Is that clear? Any doubt in this regard? Okay, so anywhere you have this particular intersect point, we are actually marking our VDS value on this current graphs. So silent. Yeah, obviously I just want you people to listen, but it seems that rather than listening, you people are staring. Is it something that you couldn't be able to understand? Is that fine, or something else you are not understanding? You can actually open up, not a problem. I think this particular plot you would have learned many number of times. I'm just trying to recollect it, that's it. Okay, nothing new that I'm telling actually. Yeah, so now what happens if I have some VGS that is greater than VT plus, I'll just increase by 0.5 again. So what happens to the new ID graph? Obviously, this new value of ID would then go somewhere over the top, right? So again, the spacing, I'm not doing it with proper scale, but the point is that the ID value would be shooting somewhere here, okay? And this is the new value of ID that I would get. Now, for this new current, what happens is that when I try to plot that current value onto this ID equation or the Vout equation, obviously the Vout would further step down, and that might somewhere intersect at this particular node or at this particular point, right? And that, if I just read out, it comes around somewhere around here, right? So this is the new value of VDS that I am getting for the corresponding input voltage that I have applied. Okay, so you obviously could be able to see that all the three relations are interlinked. What I did is that I try to vary the value of VGS, which is nothing but my VI, and that in turn was changing my current, and that change in current is being reflected in my output through this relation, and that is what I am trying to say. Okay, so rather than going right from VGS to ID and then looking at Vout, why can't we eliminate this and then try a new plot where I just plot only the VI versus Vout? Is it possible for us to do it? Right? It is possible, right? Yeah. So anyhow, I'm not going to draw it because I know that my drawing skills are completely zero. Okay, so I have just plotted for you. So this is the graph that I would get. So in this case, what I've done is that I've just bypassed the current expression, and then I'm trying to read what happens when I have my VI. The change in VI, how does it react to my output is what is being plotted here. And this graph is called as a voltage transfer characteristic graph, or in short it is called as a VTC graph, right? Yeah. I think the phenomena that we discussed before could even further applied over here as well. So what I said is that when the value of VI is less than VT, we know that this is in the cutoff, and the value of Vout would be equal to VDD, and this entire region marks that particular position. Okay, so throughout this entire region, you could be able to see that the Q1, which is the transistor, okay, which is in the cutoff region. Now, again, we had the relation of saturation just because right from cutoff, I was entering into saturation, and this is the reason why the moment I come out of this cutoff, I'm entering into the saturation regime. Okay. So after this, the Vout is dropping as I increase the value of Vn, okay, and the same phenomena is being reflected here directly, okay, without the knowledge of current, we are trying to plot it. Now at a particular spot, okay, so this is where the regime starts from here to here. Throughout this entire regime, I am in the saturation region, but there is a particular spot where I'm just entering into the linear regime, right? So the same spot is available here. Okay, this is the spot where I have actually, when I try to increase the value of Vn, I just come to a particular regime where I'm at the edge of the saturation or at the edge of the linear region, okay, or somewhere in the boundary. And the same regime could be marked on the same plot, or the Vout versus Vn plot as a point B here, okay. And after then, once you start increasing the value of Vn further beyond this particular value, you could be able to see that the slope of this particular line seems to be less slopey than compared to this line. So why is this happening? Why the slope suddenly got reduced? So one of the question is why the slope has suddenly got reduced, and the other question would be like, this particular spot, which has been marked as VOC, is not exactly equal to 0. Okay, so why is that? I think the answer to this was discussed in the last class, but still I just want to recollect both these points. What is the slope gets reduced? What happens when you have a value of VGS somewhere here? What happens to the value of VGS when you have somewhere here? So let me take this one as just as a short form. I'll take it as V1, and let me mark the second point as V2. Okay, let us reapply those in terms of output Kara. Okay, so now I'll just plot this graph of my V1. So the graph of V1 would then be something like this, right? Again, I'm not properly scaling up. And the graph of my V2, let me choose a different color, green one. Okay, so this would be my V2. So now that when I try to reduce or when I try to increase the value of Vin, these are the current graphs that I'm getting it, and obviously this line would then intersect these points at different spots. So the spots are getting intersected at these nodes, right? So when I try to read out these values, what is happening? The interval at which I'm intersecting these graphs are very tiny, right? Whereas the interval at which I'm trying to connect these two graphs are very large. So you have a larger slope over there. But as you have bunch of curves, when you try to intersect, they are being interpolated in a much smaller way. Okay, so the interpolation of this one has a major impact when you have more spacing between the points, whereas the interpolation becomes shorter or denser when you are intersecting the points at a very denser locations, okay, denser curve locations, okay, and that is the reason why we have a bit of sloppy slope over here than compared to the slope that you have got it before. Okay, is that clear? Yeah. So now what I do is that let me quickly talk about the slope of this particular line. Yeah. So yeah, one more thing is that I didn't address this particular question, right? Yeah. So why this value of VOC is not reaching the value of 0 when I restrict my input voltage between 0 to VDD. This is the range of voltage that I am applying to my input Vi, and that range is not enough for me to bring down the value of VOC to all the way to 0. So why is that? MOSFET is already switched on, or the way that I can see here is by looking at this graph. Okay, so as you have more number of voltages, say for example I have a new graph that I am plotting for a value of Vin that is exactly equal to VDD. That graph will again move something like this. Okay, so the intersection point is here at this particular point, because this is a line that we called it as a load line, and this load line will intersect at this particular spot. Is that clear? So, and the corresponding value of V in when V out when I read, it is still not equal to 0, but rather some positive quantity is what you end up. Okay, so that is the reason why you couldn't able to reach to that particular point. Okay, so we will not go much beyond this particular technical information, but we will restrict ourselves, stating that our VOC will never reach to a value of 0. Now we will hold this particular phenomena till we discuss about something known as differential amplifier, or when we discuss about folded cascode amplifier. Okay, you could able to understand, right? Yeah, so we'll just look back to the same phenomena when we discuss about a differential pair as well as folded cascode. Okay, so something will change in this particular regime. Okay, so we'll exploit that phenomena later on. Yeah, so as of now, let us try to bring our slope line. Okay, now when I try to connect all of these points, as I said in the last class, this slope has a value whose value is depends on resistance value that I've used, right? Yeah, so the slope value is given as something like -1 by RD, right? Yeah, so till this particular point we have already discussed. Now the question for you is that I'll just show one of the graph. So let me assume that the first graph is plotted with a value of R1, and the second load line was plotted for a different value of R2. Now the question is that what is the relation between this R1 and R2? Are they equal? Are they like is R1 is lesser than R2 or greater than R2? So which one is true? So R1 is greater than R2. Are you sure about this? Yeah, obviously. The R1 is obviously lesser than the value of R2. Now, you might think like, how did I get to that particular value? Just by looking at the same expression of V out, right? So because this axis is representing my V out, and I know the value of or the expression for this V out to be equal to VDD minus ID times R, and what happens is that, you see, the moment I slightly increase the value of VGS, what happens is that the current will also step a tiny bit, right? So this tiny bit of value cannot completely bring down the value of V out all the way to this particular point. So something else has to act with it in order to make sure that the V out is stepping down much faster. So which one could act along with the I to bring down the value of V out? It is the R value. So the R, if it is small, can it bring down? Obviously no, right? Because the entire product has to step down. So the only way that I can achieve this is by having both to rise at the same time. And if this rise in the current is not that much phenomenal, then what we have to do is that we have to come up with a large value of R in order to step down our value of V out drastically down. Okay, and that is what I did. So the relation that I had here, this is the one that is correct here. Yeah, so now that we have studied about this, all of these VDC graphs, now let me talk about something known as operating point. Okay, so let me just show you one of the plot here. Okay, yeah, so now the point is that there is some red spot that you could able to see over here, right? This is the red spot that I have, and the corresponding value of V in is also been marked here. So you could able to see this particular spot will happen when you have a value of V in that is equal to VT, and that particular mark is being done over here, and there is a minimum value that I'll be using it right now. Okay, now for this, what is the corresponding output that you can expect? How will I read from this graph? Just draw a line, straight line that would intersect here, and you can just read out your Y value in order to get the output, because this is my output axis right now. Okay, this is a VDC graph. Okay, do not get confused with the previous graph where we had the output on our x-axis, and right now we have the output on our y-axis. Okay, so you could able to see that this red mark corresponds to an output value that is corresponding to a value of VDD, and that is what is being marked over here. Now what happens the moment I try to vary the value of V in beyond this VT onto this graph? Let us try to answer that. What happens when I try to move? So let us assume that I have pulled the value of V in to this particular spot. Now what happens? So this corresponding value would then intersect on this graph, and this output I would be getting at the output voltage, right? So that is what the relation they share. So now what I do is that I try to vary them, and let us see some observation on this particular graph. Okay, so when I vary my input between the point A and point B, and this is my point A and this is my point B with respect to my input, and the corresponding value of output is being shown over there. Okay, so when the input is at point A, the output was at VDD, and when the input was at point B, the output was at VOB according to the graph. Okay, whereas here I just marked with a value of VD. Okay, is that clear? Yeah. So I'm not entering into the linear region, or nor I'm not entering into the cutoff region. I'm just concentrating only on the saturation. Now the point is that this particular red spot has to be fixed somewhere between this region, okay, between the point A and point B. So which region you would prefer to fix it? Would you try to answer that, or shall I try to explain it? Explain, okay. Okay, so let me just quickly read this, which is not required. Yeah, so now let us see what would happen over here when I'm trying to fix my Q point here. Now what do I really mean by the Q point is that I have a circuit, okay, and I'm trying to fix a DC potential over here. Okay, so now this DC potential is what I have right now, is nothing but is equal to VT. Okay, this is the value of VGS that I have, and the corresponding value of VGS is equal to VT, and that is what I'm fixing it here, and I'm trying to read out the value at the output as VO. Okay, so now for this we know that the current would be equal to 0, and due to which we will have this to be equal to VDD, and this is what we have learned in the previous slide. So now what I do is that I just try to have a small signal, okay, a small amplitude or a small wiggle around that particular potential of Vt. Okay. Now when I try to add this wiggle, let me try to draw this wiggle in a better way. This is my voltage axis, okay, and let me try to have a time over here, and this is my voltage axis, and the value of VGS that I have is equal to Vt. Now when I add this wiggle, now what does it do for my voltage value over a time? Yeah, it would oscillate. I couldn't able to draw it as good as possible. Okay, so the combination of these two potentials, how does the resultant graph would then look like? So I've just combined both, and let me start with the same thing. So at Vt, so I just add both these values. The value still remains the same, and at this particular point, when I try to read, the point would have got it shifted up, and again at this particular spot, the spot would have stepped down, and this is what you would have. Okay, so effectively you have a variation around this Vt, okay, which goes up and down. Okay, so say for example, if this amplitude say it is around 100 millivolt, okay, the peak value of this input would then go all the way to Vt plus 0.1, or if I fix the value of Vt to be around 0.7 volt, then the effective value that I would get over here would be 0.8, and over here the spot would be 0.7, and over here the spot would be at 0.6. Okay, so it varies throughout the entire time. Okay, and this is what happens over there. Yeah, so now let us have this wiggle, and let me try to put that the same figure over here. Okay, so this is my time axis. Okay, and over the value of Vt, I'm just trying to have this wiggle. Okay, now let us look back our output graph. Okay, so I just plot the Q point, which is right now at VDD, and this is my VO. And now how does this input reacts to my output is what I just want to learn. Okay, now during this positive cycle, what happens over here? I'm just trying to intersect with my output graph. So due to which this spot is actually get reflected at this particular point. Okay, so whenever there is a positive cycle, the same cycle is reflected at the output here. But what happens when I go for the negative cycle at this particular point? So this spot would then intersect the same value of VDD. Now how does the graph would then being built for the positive cycle of my output? Should I need to draw something like this? Can I draw like that? What is this value that I'm hitting? Same as VDD. So you cannot go beyond the value of VDD. Okay, you have to stuck with this value of VDD. Okay, so your waveform is getting clipped off. So obviously this is not a good spot to have our Q point. Okay, now what we do is that we will go to the other extreme. Probably you might have already guessed where to fix your Q point, but let me complete the lecture by having this Q point at this particular node, such that I'm trying to give a value of VGS to the DC, okay, which is given as IB, VIB. Okay, this potential I've just applied here. Now what is the corresponding output voltage that I can expect at the output? Is this graph is visible? You could be able to read the values. Yeah, what is this? VOB, right? And that is the value that I have to expect. So at the Vout, I have this VOB. Now on this value of VIB, I'm trying to add a small wiggle. Okay, so I just add a small wiggle around this particular thing, and that would in turn have some sort of the combination of both this DC and the small signal would then have this kind of variation at its output. Okay, so obviously this value of VIB is not equal to 0.7, but more than that. Okay, so now let us see how does the output reacts for it. Okay, so let me try to plot this output axis, and there's the output graph as well as the input graph over the time. Okay, and this is my V out, and this is my Vi. Okay. Now let me have the same wiggle. Okay. And for this positive cycle, when it reaches the maximum value, this maximum value is actually hitting over here, and this in turn would then reflect at the output somewhere here, right? So this positive cycle is ending up resulting in a negative cycle here, right? And what happens for the negative cycle of my input? So again, what you can do is that you can choose the minimum value of your waveform, and then that you can extrapolate it, and that would in turn would result in a intersection point, and you can just draw something like this, right? Yeah, this is a good spot. How does the positive and the negative cycle looks like? Are they alike? No, right? I'm looking at something and I'm losing something else, right? So it is not that both the positive cycle and the negative cycle are being equally amplified. Okay, so that is what the conclusion here. So now, what could be the better place to fix our Q point? Yes, around the center between point A and point B. Okay, and that particular spot is given here. Okay, now for this I need the corresponding input as VIQ. So what I do is that I'll just go here, change the value of the DC potential to VIQ, and then over that you can just try to have a wiggle. Okay, so when I do so, let me try to take off these graphs, and I try to draw the graph around this VIQ. So again, I will have a positive cycle and a negative cycle, and during this positive cycle, and let me draw the Q point at the output as well. Okay, so the corresponding Q point at the output is given by this VOQ. So I just write that, and this is my output axis, and this is again with respect to the time. So whenever there is a positive cycle, you can extrapolate this maximum value of this positive peak. Okay, and that actually hits here. Okay, and then that results in a very larger curve here. Okay, but in the negative cycle. And again, when I move towards the negative cycle, I pick this particular spot, extrapolate it, and then I bring it down here, and then this results in a positive cycle over here. Now, in this case, you could be able to see that both my positive and the negative cycle is equally being amplified. Okay, so now how far these inputs could be extended from this Q point? Are you getting my question? The question here is that what is the maximum peak value that I can have around this Q point such that I am getting a symmetrical amplification for both the positive and the negative half cycles? How far I can go up and down? Okay, so I can just go all the way till this particular spot, right? Yeah, so this positive cycle would then go results in a kind of waveform that looks something like this. Okay, so this positive cycle goes all the way down. Okay, and again the negative cycle, how far it can be extended downward? Is there any minimum spot? No? Do you really feel that? Can I bring all the way to 0? Is that is good enough? What happens when I cross this VT? Clipping will happen. I don't want any type of clipping. So what is the minimum value of input that I can have? The minimum value of this guy at the input side. I can have a swing all the way, it can reach to the tip of this value of VT. Okay, and this tip would then have an intersection point here such that I can get amplified to this particular spot. Okay, is that clear? But if I go beyond this tip, what possibly could happen is that this new graph would then results in a clipping, and then it goes down something like this. Okay, this particular spot will not be amplified, and that is what we don't want actually to be there. Okay, now usually in the questions that we would give, the spot will not be exactly at the middle. Okay, we will try to define a Q point which might be closer to the point of A or which might be closer to the point of B. Okay, and then we will try to ask you to evaluate what is the maximum input voltage that you can apply. Okay, so I'll just show one of the problem such that you have to address all of these phenomena that we have discussed onto the problem, and then let us try to solve that. Okay, so hope that this is understandable. Okay, now before we really get into the problem, I just want to spot out one of the important thing. There is something known as small signal. So we call this as a very small signal, or the incremental changes, and I generally prefer to use in terms of VGS. Okay, does it make sense? So whenever I talk about the small signal or incremental voltage, I would represent the values in terms of small letters, okay, the VGS. And whenever I talk about the DC or the Q point, I always use this capital letter, okay, like VGS. Now I also have a third form of notation, which I call it as composite form, okay, so which is a combination of both. Is that clear? And how will I write this quantity? How I can express this quantity? Yeah, it is nothing but the combination of this plus this quantity is called as a composite signal. Okay, so please remember that this is the kind of notation that I will be following throughout the entire semester. Yeah, I think yeah, probably next class we will get in, because I have to talk about small signal parameters in order to completely derive the solutions. So let me start up with the small signal parameter. Okay. So now I'll be deriving three major important small signal parameters. Those three are nothing but the GM, R0, and GMB. Okay, so you might be already knowing what are those terms and what is the expression of it, but I just want to recall all the basics that is required, so that you will not get lost when we go beyond a particular basics. Okay, so now what is this small signal model we really mean by it? Yeah. So small signal model is nothing but it's a kind of equivalent circuit which interrelates the incremental changes of like ID, VGS, or I think I should have written it as small IDs. Okay, small VGS and small VDS. Okay, so a small signal parameter, what it does is that it tries to interlink all of these small incremental changes that are happening around the circuit. Okay, and that is what our small signal model will try to do for us. Is that clear? So small signal model interrelates, okay, all of these incremental changes that are happening around the circuit. Okay, now since these are small incremental changes, what happens is that because of the small incremental changes that are happening around these parameters, the circuit elements that we use to build the small signal model are in general or linear. Okay, so we'll be using this linear elements to build the small signal model, just because these are just fine amount of incremental changes that we will try to apply. Okay, and so those are nothing but the linear elements are nothing but the resistance, capacitance, and some controlled sources. Okay, so these are the elements we'll be using in order to build them. Okay, now let us try to actually get into the real meaning of small signal parameters. Now what I do is that let me try to have I just want to know how does this incremental changes are happening across my current ID when I have an incremental changes that I'm trying to do across my VGS. Okay, so this is what I just want to relate. Okay, and possibly I want to figure out what is this guy who relates this incremental change with this incremental change. Okay, so the input side is nothing but your VGS. When you have a small increment change at the input, the output is varying, but who is controlling that variation is what we want to identify here. So Now what I do is that I'll just again try to build those relations. I just write the composite signal and I write in terms of DC as well as the AC signal, and again I can express the composite signal of the total current in terms of the capital ID plus the small id. Okay, so are you clear with the differences between all of these three terms across VGS and ID? Do you have any doubt in it? Whatever the changes are happening is what we are representing across this AC signal. Okay, so generally what I have here is the AC signal, and generally these terms are nothing but the DC value or the DC signals. Okay, and I call this entire term as the composite signal. Let me try to write the functional dependence of the total drain current in saturation. Okay, yeah, so before I do that, there is one small question. If I want to derive a small signal, which region has to be considered for that particular transistor? Saturation. You're sure about it, right? So whenever I'm talking about a small signal or small signal parameters, I'm going to assume that my transistor is in saturation. Okay, it is no other region would be considered until otherwise we force you to consider. Okay, so otherwise by default we'll all consider that the transistor is in saturation, and we'll use the required quantities from the saturation expressions, and then we'll use it for the evaluation. Okay, yeah. So now I just want to derive the functional dependencies of the total drain current. So whenever I say the total drain current, I'm actually talking about the composite current. So I just write it as small I with capital D, and that we know that it depends on many different parameters. So in short, I can just write it as K dash W by L. And how will I express this VGS? Should I since because this is a composite, should I expand in terms of composite DC or AC? Which one is the appropriate voltage term I have to fix here? Composite. Okay, so I just go with the composite signal for the VGS, and VT is a constant, so we will not have any composite signal for that, and square. And if you take into account the channel and modulation, then I will also have this. And how will I express this VDS? It's again a composite. Okay. Now, when I say the functional dependency, the value of ID is functionally dependent on these terms like VGS, VDS, and even the VSB. Now, you might wonder how does this VSB would affect my ID? Any guess? VSB is nothing but the potential difference between the body and the source. And does the current ID depends on it? Yes. Through what term? VT. So through the value of VT, if you could be able to recollect, it is dependent on VT naught gamma square root of 2 phi f. Sure. Okay, I forgot the formula, but I guess somewhere related to the VSB. So fine. Let me clear this one in the next class. What term it is. So as of now, let me just put it aside and just look for the dependency of my VT on the value of VSB. Okay. So because of that, I can also write the functional dependency not only on VGS and VDS, it also depends on the VSB term. Okay, which can again be intentionally being varied. So that's the reason why I've wrote it as composite signal here. So these are the functional dependencies that I have on the value of ID. Okay. Now, what I do is that I just want to talk about something related to Taylor expansion theory. I guess most of you might be familiar with it, but still for me to have a satisfaction, I'll just talk about it, and then later we'll use that Taylor expansion when we try to evaluate the value of ID. Okay. Now, so what I do is that let us try to consider a function y, which is defined as some function of x, f of x, and I have a plot with x and y, and let me have some sort of graph. Okay, an arbitrary graph which represents this f of x. Okay. Now, one information that I know about this graph is that for a corresponding value of x, okay, let me mark this value to be equal to c. Okay, when the value of x is equal to c, I know the exact value of output. Okay, so let us assume that the output is y1. Now, I want to build a polynomial such that around this particular regime, I just want to graph, or I just want to build a polynomial that graphs this particular function, right? So I know a particular spot's value of y, and I use that particular spot to build this entire graph by adding some polynomials around that particular regime or the known value. So let me try to build a polynomial which is defined as this, and let us go with the very least quantity, which is nothing but f of x equals to c. Now, let me use this particular polynomial to plot it. Okay, so I think it's better to use a different color. So I'll rewrite this entire thing. So I have this, and I'm using this known value to build it. Okay. Now, how does this graph would look when I vary the value of x from 0 to all the way to positive infinity? How does the graph of this p of x would look right now? Yeah, this is nothing but my y1, right? So this will look as a straight line. Does it closely resemble to anywhere to my graph of my purple? Nowhere it resembles. But what I can do for it? What I can do is that I can just try to add a slope value. Okay, if I could able to read the slope of that particular spot, then what I can do is that I can just write it as something like f prime at the value of c. I can do it. Now, when I add this extra term, the new graph would then look something like this. Okay, because since I know the value of this, what is the slope around each of these lines? It would be a kind of line along with this. Okay, but just because if I add this f prime directly with this, what would happen to the exact value at this particular spot? It gets shifted, or will I be getting the same value? Say for example, I'm trying to read a value of p of x that is exactly at c. I have to get y1. Will I get y1 when I have this kind of polynomial? Yes or no? I'm not asking something different. Let us assume that the slope value is 0.1. Okay, let us assume the y value or y1 value is 1 volt or 1. Okay, so now the point is that when I have the value of x that is exactly equal to c, does this polynomial reflects the value of 1 volt or 1 or 1.1? It reflects 1.1. That is not the one that we wanted. So what am I supposed to do in order to eliminate this 0.1 around that particular known value? Can I write something like x minus c? What happens the moment I have the value of x that is equal to 0? So equal to c, this becomes 0, and due to which this slope value would become 0, and I would get exactly the 1 when I have this p of x that is equal to c. Is that clear? And this is what is known as polynomial. Say for example, this is a quite nice graph, but say for example, if I have a spot, if I know this as my spot, okay, so this is the value of c, and for this I know the corresponding value of y1. Now, in order to really replicate the graph, you need more number of polynomials to be added, just because there are more curvatures. So whenever you have a curvature, how many derivative terms you need to add? Can I go with the slope, a single derivative? A single derivative will give only the slope. But if you want to read the curvature, what is the order of derivative you require? A second order? Yeah. So I can just add the second order derivative around the known value of c, and then you just use the same phenomena, because at that particular spot I don't want the second derivative to be disturbing the known value. Okay, due to which I multiply this x minus c. And if you have too complicated this kind of graph, what you do? You just add more derivatives to terms and then do this process. Okay, so this is known as I think I supposed to square it, right? Yeah, square and then cube, and it goes. Okay, and this is what is known as a Taylor expansion. Okay, are you clear with it? Now, So I'm just fixing it to VGS Q, which is the Q point, okay? And there is some sort of current that flows, which I mark it currently with composite signal, but when I have the DC, obviously I have to have a DC current, okay? But still, I'll just try to explain what exactly we are doing it, okay? So now, let us try to plot the relation between the ID and the VGS. What type of graph that I can expect for this? Yeah, so till the value of Vt, I will not get any kind of current, right? So obviously the graph should look something like this, okay? Now, when I fix my Q point, the Q point is at this particular notation, and let me mark this particular Q point somewhere, VGS Q, okay? And I know what is the corresponding capital IDQ, that is the current that is flowing for the device, okay? So this current which I am talking is this IDQ. I know this current. Now, I want to build the current relation between the VGS and the ID by using the Taylor expansion that we spoke about, okay? Now, can I use this known value to entirely construct the current graph around this particular spot, just with IDQ value known? I just want to build this, okay? And I have a function, okay? And that function takes in the value of VGSQ, okay? Can I use only this particular function, and that value is nothing but IDQ. For a given value of VGSQ, I know this IDQ. Now, with that known knowledge, can I construct the entire graph or not? Yeah, without a Taylor expansion. It is not possible, because if I define this as my f of VGS, okay, is equal to IDQ, then whatever the value of VGS that I apply, this results in a constant graph, okay? This is not an exact replication, but I want to exactly replicate this this particular graph that I normally get it around my Cara, input Cara. So what am I supposed to do for this? Yeah, I can add the slope term, right? So I can just have a slope term, which is nothing but the slope around the known value of VGSQ, and to that I also have to add, yeah, okay, which is nothing but the small signal, okay? So the small spot, which I write it as VGSQ, okay? The difference of the value, okay? So around this particular known value, I'm just trying to have a wiggle, and this amplitude is represented by this VGSQ, or the difference between the known value and this value, okay? This difference is read as a VGSQ, okay? Was that is clear? X minus C, where X is this quantity and the C value is this quantity, and the difference between the X minus C is read as small VGS. Is that is clear? Yeah. So now let us try to figure out this particular term. Now how do I do this differentiation of this? What I'm actually doing is that the differentiation of the f prime of VGS is nothing but the derivative of this quantity, derivation with respect to which function? Yeah, VGS, okay? So this VGS is evaluated only at a spot where this VGS is equal to capital VGS. So rather than writing a derivative like this, I can map this derivative to be written as this divided by this quantity. It is exactly the same thing, okay? I have replaced this composite signal of my VGS with the known value of VGS, which is the DC value, okay? It has been evaluated around that particular spot. So in general, the composite signal could be returned as this quantity, which is the IDQ, plus, sorry, I have mixed the term. Is that clear? Or if you are still not convinced with the way that I have written down, you can still replace this capital IDQ as the value of IDQ at VGS that is equal to VGS, capital VGS, because I know that value. So what is that value? It is nothing but IDQ plus this. Now what is this quantity generally? a derivative of ID with respect to VGS? Yes, conductance, okay, or transconductance, because we are weighing the input and looking at an output, right? So there is a transfer between the input and output, and that's the reason why we have it as transconductance or GM, and this VGS. Okay, so all of these things. Now, why did I stop towards the first derivative? Why I didn't go for further higher terms in the derivative? The graph is very simple, right? Because once I know the derivative, it gives me the slope. I can exactly replicate it. If I go for double derivative, it doesn't reflect my original graph. Okay, so it is enough for me to stop till the first derivative. I don't need to go for double derivatives and stuffs. Okay, and that's the reason why we stop it over here, provided if the value of VGS is so small. Okay, the small VGS is there, right? If this is quite smaller, then I can restrict with the first term itself. Clear? So now I will come back to the same thing. This term is nothing but my composite signal. I can write this composite signal as a summation of two terms. One is the DC current, the small signal current. And what is this small signal current? How do I write? What is the relation that they share between this quantity and this quantity? The small ID is nothing but GM VGS. How will I expand this term? This ID, because it's also a function of VGS, right? So how will I write that function? The capital ID. What is this then? Half Kn dash. So whatever we wrote, I don't know how many people observed, like whenever I was writing this half Kn dash term, I was using the capital letter just to denote that it was a DC signal, and I can evaluate just because I know this guy. Okay, and again you see that I'm using the capital VGS, okay, because I have to write down this particular term at a value of VGS that is equal to capital VGS, okay, and that is the reason why I've replaced this with that. Clear? Yeah. So now, obviously we have to come up with the answer for the GM, okay. So the value of GM is nothing but ID by small signal ID by small signal VGS, but, or I can even write it as this quantity, or okay, so these are many different forms. Now what I do is that since I need an expression, or I would use this form or this form in order to derive it. Okay, so let us try to do that. So I want to derive the value of, or the expression for this GM, due to which I do a derivative across the ID term for a constant value of VGS. Okay, now what is this ID? How will I write this ID? So I could write it as half Kn dash W by L, which VGS? Okay, composite only, I have to write it, minus VD the whole square. But what I said is that I'm just going to make a derivative with respect to a value of VGS where this composite signal is being evaluated only at capital VGS. So what I'm supposed to do is that before I substitute here, I just replace this composite signal with the capital VGS, and then I try to do the derivative. So when I do the derivation of this ID, what is the term that I would end up having it? The square term, because this is my capital VGS that I have. So x square is nothing but, when you derive it, 2x it will come, right? So due to which, what is the term that you would end up having it? Yeah, Kn dash W by L, capital VGS minus VT. Now, you see, I have derived the small signal parameter GM. We know it's a small signal parameter. But when I look across the term that is used to evaluate that expression or that particular parameter, is this parameter is a composite? No. Is this value of VGS is a small signal? No. But what is this VGS then? It's a DC. You see, I will also show for R0 as well as GMB that whenever we try to evaluate these parameter values, even though they are called as small signal parameters, we have to evaluate based on the DC value that I have, or the Q point, around which Q point I'm operating in. Only if you know the Q point, I can evaluate each of these small signal parameters. Otherwise, no information is given to you. So the most important thing is that to do this, you have to have the Q point information. Otherwise, you cannot spot it out. And I have proved through a derivation. That's it. Okay.